Have you ever wondered how a self-driving car knows exactly when to hit the brakes, or how scientists can predict the path of a comet light years away? Well, it all boils down to the fundamental physics of how things move. And today, we're going to build the essential toolkit for understanding all of it right from the ground up.
Just think about it for a second. Motion is literally everywhere, from the epic, swirling dance of an entire galaxy, all the way down to the blood flowing through your own veins. The entire universe is in a constant state of motion. It's the one thing that connects everything at every possible scale.
So it's one thing to watch a car drive past, but it's a completely different challenge to describe its movement with the kind of precision physics demands. How do we create a language that can predict exactly where that car will be, how fast it's going, and when it's going to get there? Well, that's exactly what we're going to figure out today.
So here's our game plan. We'll start by defining what motion even is in the first place. Then, we'll zoom in on the idea of speed at a single instant. After that, we'll tackle acceleration, how things speed up and slow down. Then comes the really cool part. We'll reveal the physicists' magic equations. And finally, we'll use them to understand something that could literally save your life.
All right, so to build this language of physics, we need to start with a rock-solid foundation. In science, being precise with our words is everything. It gets rid of any confusion and lets us build these big, complex ideas on something we all agree on.
And here it is, the big one. In physics, motion is just a change in an object's position over time. It sounds almost too simple, right? But believe me, this one simple idea is the seed that our entire understanding of how things move grows from.
Now think about a road trip. If you drive 100 kilometers in 2 hours, sure, your average speed is 50 kilometers per hour, but that doesn't really tell the whole story, does it? You are probably stuck in traffic at some point, then maybe speeding up on the highway. We need to get way more specific. And this brings us to a super important distinction. Average velocity is the big picture. Your total displacement, which is just the straight line distance from start to finish, divided by the total time. It's the summary of the trip. But instantaneous velocity, that's what your speedometer is showing you at any given moment. It's your speed, right now.
So how in the world do we nail down the velocity at one specific instant? Well, this is where calculus gives us a kind of superpower. Imagine calculating your average velocity over shorter and shorter time intervals. First over a whole second, then half a second, then a millisecond. As you shrink that time down closer and closer to zero, the number settles on one precise value. That's the limit, or what we call the derivative. That dx over dt you see there is just a fancy way of saying a tiny change in position over a tiny change in time.
This whole thing becomes so much clearer when you can actually see it. If we plot an object's position versus time on a graph, the instantaneous velocity is just the steepness, the slope of the line at any single point. A really steep slope means you're moving fast, and if the slope is totally flat, well, your position isn't changing, so your velocity is zero. Simple as that.
Okay, so now we can describe an object's position and its velocity at any instant. But in the real world, things rarely move at a perfectly constant speed. So that brings us to the next big question. What happens when that velocity starts changing?
Well, that change has a name: acceleration. And there's a beautiful pattern here. Just like velocity is the rate of change of position, acceleration is the rate of change of velocity. And we use the exact same idea from calculus. It's the derivative of velocity over time, or dv dt.
Now, this is a huge point that trips a lot of people up. Acceleration is not just speeding up. Since velocity has both speed and direction, if you change either of those, you are accelerating. So hitting the gas pedal is acceleration. Hitting the brakes is also acceleration, just in the negative direction. And even taking a turn at a perfectly constant speed is acceleration, because your direction is changing.
And we can see this on our graphs too. If the position time graph is curving up, kind of like a smile, that means you've got positive acceleration. You're getting faster. If the graph curves downward, like a frown, that's negative acceleration. You're slowing down. Okay, we've got our three core building blocks: position, velocity, and acceleration. Now for the really fun part. Let's put them together to build a powerful toolkit that lets us do something that feels a little bit like magic: predict the future. This is where the real power of physics kicks in. For any situation where acceleration is constant, like an object falling under gravity, we don't have to guess what's going to happen. There's a special set of formulas, the kinematic equations, that can tell us its exact position and velocity at any time we want. And here they are. These three are the keys to the kingdom. Let's quickly meet the players.
x is for position, t is for time, a is for acceleration, v is our final velocity, and v0, we usually say v0, is the initial velocity. Each equation is useful for a different scenario, but here's the magic trick. As long as you know any 3 of those 5 variables, you can use these equations to find the other 2, every single time.
So these equations are cool, but they aren't just for a textbook. Let's take our new toolkit and use it to understand a situation every single one of us faces, slamming on the brakes in a car.
When you hit the brakes, your car doesn't just stop on a dime, right? The distance it continues to travel while it's slowing down is called the stopping distance. And understanding this isn't just a fun physics problem, it's absolutely critical for things like setting safe speed limits.
Let's model this with our toolkit. So we have an initial speed, our v0. We know our final speed, v, is going to be 0 because we're stopping. The brakes give us a constant negative acceleration, minus a. The thing we want to find is the distance, x. See how we don't know anything about the time? That's a huge clue. It tells us to grab that third equation from our toolkit. We plug in 0 for the final velocity, do a little algebra to solve for x, and bam, we get this formula.
And this simple formula tells us something incredibly important, something that isn't obvious at all. Because that initial velocity term, v0, is squared. The stopping distance isn't just proportional to your speed, it's proportional to the square of your speed.
So what does that actually mean? It means if you double your speed, say you go from 30 to 60, you don't just need twice the distance to stop, you need 4 times the stopping distance. Let that sink in for a second. That is a massive difference. This isn't just some traffic rule, it's a fundamental law of physics, and it's exactly why speed limits save lives.
So we started with the simple act of a car braking, and we ended up uncovering a universal language. The exact same equations we just used also describe the arc of a basketball, the orbit of a satellite around the Earth, even the path of a comet across the solar system. The universe is speaking in the language of motion. And now you understand the grammar. Thanks for tuning in.